sure you've seen probability theory in some context or the other. In today's lecture, we're just going to quickly review this theory. And let us begin by looking at this cartoon, which illustrates an important aspect of probability theory. A lot of times, there are some misconceptions in in people's understanding of probability theory, and as a result, they have a tendency to apply it in inappropriate ways. This is not just true of probability theory, it's also true of statistics as a whole, and also, in fact, larger mathematics as a whole. But the cartoon quite nicely illustrates how a misunderstanding can lead to funny and inappropriate ways of applying the theory. So take a moment, pause, enjoy the cartoon, and continue. So now in order to understand this theory, let's start from the very basics. Let's start from the axioms of probability theory. And for that, we have to be clear about some basic definitions. And let's start at the very heart of probability theory, which is an experiment. What is an experiment? It's simple. It's just an activity that leads to a well-defined set of outcomes. So an example of an experiment could be rolling a die, or tossing a coin, or running a randomized algorithm, and so on and so forth. And so these outcomes that we're talking about are the various possibilities that we can encounter as a result of the experiment. Now, a clear understanding of these possibilities is very important, and we in fact have a very good term for it. We call it the sample space. This is simply the set of all possible outcomes when you run an experiment. Okay, so here's an experiment rolling two dice, and the set of all possible outcomes is let's suppose we are interested in the sum of the numbers that occur in both those dice as after we roll them. So the possible outcomes are 2, 3, 4, up to 12. Of course, one is not possible because both the dice will at least have the number 1 on their faces. So the sum of them is at least going to be 2. So each of these outcomes is basically a what is called a simple event. And so in this particular experiment, we have 11 possible simple events. And sometimes these simple events are also called sample points. Okay? And as we mentioned, the sample space is simply the set of all possible outcomes. Now, sometimes we may not be interested in these simple events, the elements of the sample space. Sometimes we're interested in other events that are basically subsets of sample space. So let's give ourselves an example. Suppose consider the event E is the event that outcome is a prime number. And so this E is now either 2, 3, 5, 7, or 11. And of course, this is a subset of the sample space. Okay. And these events are useful because now we have the freedom to define these events, and we can define it appropriate to the context in which we are interested in. Okay, now that we have introduced the various possibilities, the sample space, now we have to introduce the notion of probabilities, the likelihood with which each of the events in the sample space occur. So for this, we will have to define a probability space, and the probability space consists of 3 components, the first 2 of which we've already seen. The first component is simply the sample space. So we should have a very clear understanding of what the experiment is, and therefore what the set of all outcomes is. And then, knowing the sample space, we must also know the set of all events that we are interested in. and these events that we are interested in is captured as a family of subsets, family um, F of subsets of the sample space omega. And each element of this family is an event that is of interest to us. Now we need to define a probability function. It's basically a function that maps each event to a real valued number, and this probability function must obey some basic axioms. First of all, probabilities are a measure of likelihood, and they range from 0 to 1. If it is 0, then it's impossible for that event to occur, and if it's a 1, the event must occur. So for example, the probability of let's say the event we are interested in is in fact the entire sample space omega, then one of the outcomes must necessarily occur, and therefore the probability of the sample space itself must always be 1. And any other event must have a probability that's either 0 or something in between 0 and 1 or 1. Okay? It can never go outside of this range 0 to 1. And finally, we want these probabilities to also obey this rule. Now, if you look at disjoint events, the probability of the union of these disjoint events. So here the disjoint events are E1, E2, and so on. The probability of the union of the events must equal the sum of the individual probabilities. So now if we have such a probability function defined on top of a sample space and a set of events, then what we have what we call a probability space. And the entire probability theory rests on understanding probability spaces. These are very fundamental notions, and everybody must have a clear understanding of this probability space. Okay. And just a quick exercise. We talked about these events being finite or countably infinite. We've also seen a probabilities or a sample space where it had a finite number of events, simple events, rolling two dice. Can you think of a natural experiment where the outcome is a countably infinite sequence of events? So before we end this segment, let us look at a couple of fundamental principles that are very useful in probability theory. The first one is the inclusion-exclusion principle. This actually comes from the inclusion-exclusion principle in set theory. Let's say we have two events, E1 and E2. The probability of their union is equal to the probability of the first event E1 by itself plus the probability of E2 by itself. But then we've done a little bit of overcounting, so we have to do this a small correction, and so we have to subtract out the probability of their intersections. This is classic inclusion-exclusion principle, and this I'm sure you've seen this in the context of probability theory, set theory, and it shows up here in probability theory as well, of course. And you may recall that this principle can be generalized to more than two sets, or in this case more than two events. And so a quick exercise would be to write down the formula when you have not just two events but some n events. A simplification of the inclusion-exclusion principle called the union bound turns out to be very, very useful. To motivate the usefulness, consider a set of events, E1, E2, etc., there are bad events, and you don't want these events to occur. You want to show that the probability with which these events occur is very, very small. And so we are obviously interested in upper bounding the probability of the union of these events. That's what we have on the left-hand side. We could use the inclusion exclusion principle, but the formula gets pretty messy, especially when the number of events is more than two. However, there's this nice simplification. The right-hand side need not be as complicated if all we want is an upper bound, and for a lot of purposes, this upper bound is sufficient. All we all we need on the right-hand side is the summation of the individual uh, probabilities. Because if you sum the individual probabilities, there might be some overcounting, but if we are careful with bounding the individual probabilities for a lot of applications, that's sufficient in order to give us a good upper bound. In other words, a small upper bound. So throughout this course, we will be applying the union bound in several contexts. This tends to be a very useful principle in a lot of algorithmic analysis.